Hello, this is Adolf. Welcome to the video lecture series on the course of Design of Steel Structure. In this video, we are going to start our unit number 6, that is beams. Under the unit number 6 beams, we have to see what are the different steel sections used as beams, what are the design criteria of beams, and what is the design procedures and how we have to design and analyze the beams. These topics we are going to see in the unit number 6. But in this video, we are going to see about introduction, what are the different steel sections used as beams, and what is the design criteria of beam. In that, we are going to see particularly design of bending moment only in this video. The remaining design criteria we will see in the upcoming videos. Let's start our video with introduction. So what is beam? What is beam? So beam is a structural member subjected to transverse loads. So what is the transverse loads means in the diagram, which is perpendicular to the longitudinal axis. It is perpendicular to the longitudinal axis. So if it is parallel to the longitudinal axis, then we will call it as an axial load. So if it is perpendicular to the longitudinal axis, we will call it as a transverse load. So if any member that is subjected to this transverse load, we will call it as a beam. These beams are the most critical members in any structure. So if you take any structure, this beams only the most critical member. It will be fail due to the heavy loading. So we have to be design this beam not only up to economical, but also we have to design it for the safe. So if if any building, if you are going to design, we have the beams are the very critical section. So we have to be consider the safety of the beam. Beams are mainly of two types. One is simple beam like this, I sections. Mostly we will use I sections as the beams. So simply an I section. So that is a simple beam. Second one is built up or compound beam. That is, we are using I section and that we will introduce one more section to it. Mostly a plate we will use. So we are placing a plate over the I section. That is, two sections of we are using in for a beam. So that type of beams we will call it as a built up or compound beam. So beams are classified into many types. So we will see one by one. First one is major beam. So major beam is, see in the diagram, this part we will call it as a major beam. These major beams of a floor system usually supporting joist in building. So this major beam will comes in the floor system and is used to support the joist. This one is joist. So above joist we will lay down our floor. So this major beam will hold the joist. Second one is girder beam. So these girder beams are same as the floor beam, but it will in the lengthwise in the building it will be given. So that's why it is called as a girder beam, and it is also the major beam in the structure. Third one is grid. So grid is a horizontal member fastened to and spanning between peripheral columns of an industrial building. So this grid will be used in the industrial building only. So see here, this is one column. This is one column. Between these columns, we are having this this is the grid. This is the grid beams. So we will give the grid beams. Why we are giving this grid beam means to support wall claddings. So we have to support the wall claddings. So your height will be more. So we are giving the intermediate beam, that is called grid beam. Next one is joist. So we know joist is the beam that is supporting the floor construction, but it is not a major beam. So this is the joist. So this one is major beam or floor beam. This part is guider, and this beams are called as joist. These beams are called as joist. Next is lintel beam. So where this lintel beam comes is, it will comes over the wall opening. Wall comes under the over the wall openings, like door openings, door or window. Above door or window, there is a wall opening. In that we will have this lintel beam. So the main function of this lintel beam is, this beam used to carry the wall loads. So wall loads over the wall opening. So this is the wall, and we have a lintel beam. So these portions and all wall, everything is wall. So this load from these loads will be carried by the lintel. Next is purlin. Purlin is a roof beam usually supported by roof trusses. So in the roof trusses, this is purlin. So mostly we will see this purlin in the roof trusses. Second one is a rafter. Same as in the roof beam, we will see this rafter. This rafter will support the purlins. So purlins is supported by roof trusses, and this purlin rafters, these rafters also supporting the purlins. So this part is called rafter. This one is purlins. So these purlins and rafters will come in the roof trusses. Next, stringers. This stringers, it is a beam that's supporting these stair steps in case of building. So we mostly see these type of stairs. In between we will have a steel section. This steel section we will have a staircase, stair steps we will have. So this steel structure we will call it as a stringers. Mostly we will see in some modern buildings. So for architectural as well as aesthetic looks, it looks good where we'll have one straight sections. So that is called stringers. Next is spandrels. Spandrels is exterior beam at 4 level of the building. So see here, this is the roof or floor. If this is considered as a roof, this is the exterior part. This part is exterior. So this part we will call it as the spandrels. Or if you take the building, say this is the exterior part. These are all interiors. This one is exterior part. So this exterior part we will call it as a spandrels. So why we need a spandrels means, this will carry some part of floor load and the exterior. So it will carry some part of floor load and exterior wall. That is the uses of the spandrel. Last one is header. So header is beam at stair well opening. So these header beams will be used where means when you are going for the stair openings, at that place we will have a header. So see in the diagram, so this part is the well opening for the staircases. So this part is called header. So these two beams are called as headers, and this side, this two will called as a trimmer. Trimmer and headers, the position is changed. So that is our header and trimmer. What are the different sections, steel sections, which are used as a beam? We have I section. This is also wide flange I section, C section, angle section, T, plate, rectangular, or solid or circular. These are the different sections we used for the used as a beam in a steel structure. So if you are if you are going to use a rolled I section or a beam section, we use this rolled I section or a beam section in floor beams, joist, stringer, spandrels, or grider beams. We will use this rolled I section or a beam section. So if you want to use the rolled channel section, we will use for secondary beams such as purlins, lintels, grids. These areas we will use the rolled channel section. And if you want to build up beams in your building, where we will use the build up beams means we will use this build up beams in the floor beam only. But when we use that means the depth of the beam to be restricted. So suppose if your design part, the depth of the beam is coming as 2.5 meter, just assume. So you want to reduce the depth of depth, then we want to reduce to 1 meter, means we will reduce by using built up beams. That area we will use this built up beam. And final one is plated beams. So these plated beams will be used for guiders. Guider, we will use this plated beams also, and it is built with the rolled plates. We will build the plated beams. So these are the different sections we are using. Till now, in this video, we saw the basic introduction and what are the different sections used as a beam in a steel structure. So now we are going to the we are going to see the design criteria of a beam. So what are the design criteria we have to consider while we designing a beam? There are three major design criteria we have to consider. First one is a design of bending moment. Second one is design of shear force. Third one is check for deflections. These three are the major design criteria of a beam. So in this video, first we see the design of bending moment. The remaining two we will see in the next video. Design of bending moment. So under the design of bending moment, we will find out what is the bending stresses and the moment of resistance. So we will find the bending stresses and the moment of resistance. So how we will find the bending stresses? The actual bending stresses, that is sigma BC calculator, that is in compressive. Sigma BC, if it comes, means it is in a compressive. Sigma BT, that is in tensile. So calculator. How we have calculated means sigma BC or sigma BT, that is equal to M by I into Y. M by I into Y. And we know the modulus of section Z is equal to, what is it? Z is equal to I by Y. So here we substitute this modulus of the section in the above equation. So the above equation will come as M by Z. So sigma BC or sigma BT calculation is equal to M by Z, where M is the maximum bending moment. So maximum bending moment, we can calculate what type of beam we are going to use. It is a simply supported beam, or it is an cantilever beam, or overhanging beam. According to that, we can calculate the maximum bending moment. I is moment of inertia of the cross section of the beam throughout bending axis. So throughout bending axis, what is the moment of inertia? and y is the distance from neutral axis. So this is your beam cross section. So this is your neutral axis. This is your neutral axis. So y is the distance from the neutral axis here to here. If it is in compression, this is the neutral axis for the compression flange. Or if you are considering the tension flange, then this will be the your neutral axis to the tension flange. So y is the distance from the neutral axis and z is the modulus of section. So if you are considering it is in compression, so this is your beam neutral axis. So if you are considering for the compression flange, this is a tension flange. So if you are considering the modulus of section for a compression flange, then z is equal to I by yc. So yc is distance from axis of bending to extreme compression flange. So assume the bending is from the neutral axis, then your compression yc is, this one is the yc value. So if it is in tensile, then your z value is I by yt. So yt is neutral axis to tension flange. This is yt. So distance from axis of bending to extreme tension fibers. So these are the section modulus we can get. If sometimes you know the z section section modulus z and sigma bc are given, then what is the moment of resistance? How we can find the moment of resistance? So moment of resistance is m suffix r. So how we can find means sigma bc into z. Sigma bc into z. If the allowable bending stress sigma b is given and the z is required, means from the above equation z required is equal to m by sigma bc. So m is the maximum bending moment divided by sigma bc. So this is the design of bending moment. But what is the permissible bending stresses? We know sigma bc, we are using sigma bc or sigma bt. So we have to consider this, how we can know the permissible bending stresses. Suppose there are two beams are there. One is laterally restrained beams, another one is laterally unrestrained beams. So laterally restrained beams means, so this is your I section. So this is the compression flange. So this compression flange will be fitted into the concrete. So it will be fitted into the concrete. So what will happen? This won't move freely in the direction. Like this, it won't move freely. So it is laterally restrained. So lateral movements are restricted due to the concrete was due to the compression flanges inside the concrete. So it will restrain against the buckling. So buckling won't much happen in this for laterally restrained beams. So if you consider our beam is an laterally restrained beams, then our permissible or allowable bending stress for both compression and tension, it will be equal same. So sigma bc and sigma bt will be same for laterally restrained beams. So it will be is equal to 0.66 fy, 0.66 fy, where fy is the yield stress of steel. So yield stress of a steel. So if it is in a laterally restrained, our sigma bc or sigma bt is equal. So their value is 0.66 fy. Second one is for a laterally unrestrained beams. So laterally unrestrained beams means the compression flange is not restrained against buckling. So due to the buckling, it will move some lateral directions. So in that, your sigma BC is not equal to sigma BT. So the permissible tensile bending stress sigma BT is equal to 0.66 Fy. But your sigma BC is differ. So for a laterally unrestrained beams, the sigma BC is depends on yield stress, lateral support condition of a beam, and slenderness ratio. So this sigma BC formula is given. It says 0.66 Fy FCB divided by Fy power n plus FCB power n to the whole power of 1 by n. This whole term should be less than or equal to 0.66 Fy. 0.66 Fy. So where this formula we studied earlier, we have studied this formula in the unit of compression members. So your sigma in the for a laterally unrestrained beam, the compression members, it will act as a compression flange will be act as a compression member. But in a laterally restrained beams, both are same. But here unrestrained, sigma BC is differ and sigma BT is differ. So we know Fy is yield strength. FCB is elastic critical stress in compression. Elastic critical stress in compression. How we will find the sigma BC, sigma CB, FCB, that is equal to pi square EI by slenderness ratio KL by RYY square or RYY square. So our sigma BC, it depends on Fy, slenderness ratio, and Fy and slenderness ratio. So in this video we saw what is the introduction to our beams and what are the different sections we use, and we saw the one major design criteria, that is bending moment. So how we have to calculate that one. So in the next video, we see the other two design criteria, and let us do some problem in the next videos. Thank you.